The thing with row reduction, though, is that it can only take us so far. Actually, I should walk that back. Row reduction could be used to do everything in the third problem as well, finding a basis for the column space of a matrix. What you would have to do first is potentially transpose the matrix A into A transpose, and then use the row space algorithm on the rows of A transpose, which would then be the columns of A, and you would get something similar. But I'd like us to think of a way in which we can find a basis for the column space of A without having to transpose the matrix first. So let's say you write the matrix in column blocks. Column 1, column 2, all the way up to the nth column. You'll try to collect as many linearly independent columns as possible, going from left to right, and you're going to discard the columns that are not as you encounter them. And this is something you can actually do by working with the reduced row echelon form of A, not the RREF of A transpose. Okay, so how would we find a basis for the column space where A is this matrix here? 1, 2, 2, 3, 2 minus 2 minus 8, 4, 1, 1, 0, 1, and 0, 2, 4, 1. So basically, we're looking at all linear combinations of these 4 columns. What does that look like? Is it a 4-dimensional space? Is it a 3-dimensional space? And so on. So we collect the linearly independent columns of A from left to right, getting rid of the columns that are not linearly independent as we go through the process. So we write the matrix A as a collection of 4 columns, C1, C2, C3, C4. Let's assume that C1 is not the 0 vector. Then C1 is linearly independent. But does it span the entirety of the column space of A? Well, we know that it could, and a good chance it won't, and not impossible. How do we know this? Like if C2 is in the span of C1 in general, then there's at least a chance that the set C1 is a spanning set for the column space of A. So let's verify. In this case, it doesn't. In fact, if we take a look at the matrix we have here, the second column is not a multiple of the first column, so they're not in the same span. When you have 2 vectors, it's easy to tell. But we might find it a good idea here to introduce a method, an approach that will be useful later. So is C2 in the span of C1? It will be in the span of C1 if and only if, when you look at the linear system with augmented matrix C1, vertical bar C2, that as a system is consistent. And that's going to be true if and only if the rank of C1 augmented C2 is exactly the same thing as the rank of C1. When you row reduce the augmented matrix, just C1, C2, you actually get 1, 0, 0, 1, 0, 0, 0, 0, which we recognize as being in reduced row echelon form. Now the rank of C1, C2 in this case would be 2 because you have 2 pivots. The rank of C1 is just 1 because there's only 1 pivot in C1, whereas there's 2 pivots in C1, C2. And that tells us that the system in question is not consistent, or in other words, that you cannot write C2 as a linear combination of C1. So C2 is not in the span of C1. C1 and C2 are thus linearly independent. The span of C1, C2 is genuinely bigger than the span of C1. So we would keep both C1 and C2 as vectors in the basis of the column space. The next step then would be to say, okay, I'm going to go to C3. I want to know if C1 and C2 might actually span the entirety of the column space of A. If that's the case, then you would definitely have that C3 would be in the span of C1 and C2. You wouldn't need it, it'd be redundant. So that's going to be true if and only if the augmented matrix C1, C2, C3 is the matrix of a consistent system, which is the case if and only if the rank of the augmented matrix is the same as the rank of the coefficient matrix. All right, so let's do it. C1, C2, C3, that's the matrix 1, 2, 2, 2 minus 2 minus 8, 1, 1, 0, 0, 2, 4. Put the vertical line here to remind us that we are looking at a augmented system. And then we reduce this. Well, the good thing is we've already done some of the work, or at least we can keep the same operations as the ones we were using for some of it, right? And we'll get 1, 0, minus 2, 0, 1, 2, and a bunch of zeros. What do we know here? Well, this system is consistent. It has at least one solution. It has a rank augmented of 2 because there are 2 pivots, and the 2 pivots are in the coefficient matrix right here. Whereas in the previous case, that is not what we had. In the previous case, there was a pivot in the augmented column. Here, I don't have a pivot, a leading one in the augmented column. So that tells me that C3 is in the span of C1 and C2. I can write C3 as a linear combination of C1 and C2. So the span of C1, C2 is exactly the same as the span of C1, C2, C3. Might as well get rid of C3. It doesn't give me new information for the column space of the matrix A. The next question I ask is C4 in the span of C1, C2? That's my last possible column. Well, I know that span of C1, C2 is the span of C1, C2, C3. So this question is the same as asking, is C4 in the span of C1, C2, C3? That is going to be the case if and only if the linear system that corresponds to this augmented matrix is consistent, which is to say, if the rank of C1, C2, C3, C4 is exactly the same as the rank of C1, C2, C3, without having the fourth one. But that's not the case. If I look at the reduction of C1, C2, C3, C4, I'm going to get 1, 0, minus 2, 0, 0, 1, 2, 0, but 0, 0, 0, 1, and 0, 0, 0, 0. Now you have to do this to convince yourself that this is the case. 3 leading ones, but one of them is in the augmented part of the matrix. So that system is inconsistent, and that tells us that the rank of C1, C2, C3, C4 is greater than the rank of C1, C2, C3, and so that C4 is not in the span of C1, C2. So I have to keep C4. C1, C2, C4 is going to be linearly independent, and its span is the same as the span of all the columns, which is the column space of A. So C1, C2, C4 is a basis for the column space of A. Now, the warning is you keep only those columns of A. You don't go and look at the columns in A tilde, or the RREF of A. You use the RREF of A to find the columns that have leading ones, and you go and grab the corresponding columns in the original matrix A. We have a theorem about this. If A is an n by n matrix, the columns of A, which give rise to leading ones in any row echelon form of A, they do form a basis for the column space of A, and the dimension of the column space of A is going to be the rank of A, the number of leading ones in your matrix. I mean, basically all we have to do is to formalize the algorithm that we used in the previous example. So we write A as a bunch of columns, U1, U2, all the way to UN. We choose a subset of the columns of A, which are a basis for the column space of A, as follows. The first thing we do is we find the row-reduced echelon form of A. You start with U1. If U1 is the 0 vector, then you discard it. It cannot be part of the basis. Otherwise, you keep it. The next thing is you look at U1, U2. If U2 is in the span of U1, then the set U1, U2 would be linearly dependent, and span U1, U2 is just span of U1, so you get rid of U2. Otherwise, you keep U2. And you do the same thing with U3. You look at U1, U2, U3. If U3 is in the span of U1, U2, then it is redundant and you discard it. Otherwise, you keep it. And you continue in this way, deciding at each step whether the vector that you're adding is one you keep or you throw it out until you've gone through all the vectors. At the end of this process, you have only linearly independent vectors that span the column space. Now we check linear independence at each step. So the only things that were removed were vectors that were in the span, so vectors that were linear combinations of the ones we kept. But why do we bother finding the row-reduced echelon form of A? Well, it's because there's a way to speed up this process. Once you've done the RREF, once you've computed it, you can use it to decide which vectors to retain and which ones to discard. You don't have to do this step by step or algorithmically. Like if you wanted to know whether UK was in the span of U1 to UK minus 1, you'd row reduce the augmented matrix and you verify if you can write this as a linear combination of the other ones, or, in other words, is this augmented system here consistent? So you'd be looking for a leading one in that last column. But you don't actually have to row reduce again, right? You could just look at the first k columns of A tilde, the reduced row echelon form of A. If the kth column has a leading one, then the system would be inconsistent, and you would conclude that UK was not in the span of U1 to UK minus 1, and so you should retain UK. Otherwise, UK should be discarded. So the conclusion to that is you keep UK in the basis of the column space of A if and only if there is a leading one in the kth column of A tilde, the reduced row echelon form. And this rank A such vectors in the basis because each of these corresponds to a column of A, and this is important here, column of A that had a leading one in the reduced row echelon form. As a corollary, if you have a matrix A and you look at its transpose, A transpose, then the rank of A, which is the number of leading ones in the reduced row echelon form of A, that's the dimension of the row space of A, number of rows that get retained when we reduce matrix. It's also the dimension of the column space of A. And by the nature of A transpose, that's the dimension of the column space of A transpose, the dimension of the row space of A transpose, and the rank of A transpose. This is a pretty amazing result, actually. It doesn't matter the size of the matrix, the total number of independent rows is going to be the same as the total number of independent columns. It didn't have to be this way. That's the way it works out. But that's interesting. That's impressive. So how would we find a basis of the column space of A for this matrix A? Here has 3 rows and 5 columns. You find the reduced row echelon form of A. I tell you that this is the reduced row echelon form of A, but as always, you're going to have to go and verify that this is indeed the case. Where are the leading ones? First, second, and fourth column. So then I go back to the original first, second, and fourth column, and these would form a basis for the column space of A. 2, 3 minus 1, 1 minus 1, 1, and 3, 1, 1. What about this one? Find a basis of the column space of A for the matrix 1, 2, 1, 1, 2, 1, 1, 2, 1. Well, you compute the reduced row echelon form. It's going to take you to the matrix 1, 1, 1, 0, 0, 0, 0, 0, 0. And notice here I originally read those as columns, but typically the tendency when you reduce the matrix is to view them as rows. That's just a natural tendency because we spend so much time talking about elementary row operations, say. So according to this, there's one leading one in the first column of A tilde. That's the matrix A tilde, right? The reduced row echelon form, and that corresponds to the first row of the original matrix, first column of the original matrix A. 1, 2, 1 is a basis then for column space of A. But the first column, the reduced row echelon form of A, this one here, is not a basis for the column space of A. It's not even in the column space of A, actually. For column space of A, you have to go back to the original A. What about this one? What if we had U, which was the subspace of R4 spanned by these 4 vectors? 1, 2, 1, 0, 2 minus 2, 1, 2, 2 minus 8, 0, 4, and 3, 4, 1, 1. Let's find a basis for U, which is a subset of this specific spanning set. So you could put this in the rows of a matrix, reduce, use the row space algorithm to solve the problem, but here we're going to use the column space algorithm because that's also something you can use. So you build a matrix A, its columns are the given vectors. 1, 2, 1, 0, 2 minus 2, 1, 2, 2 minus 8, 0, 4, and 3, 4, 1, 1. We've worked with this matrix before. We know what its reduced row echelon form is. It is the following matrix. If you go back to the original matrix A, you will find that a basis for column space of A, which is this subspace U that is spanned by the columns, would be 1, 2, 1, 0, 2 minus 2, 1, 2, 3, 4, 1, 1. Remember when we looked at the row space of this matrix here, space W, it also had dimension 3.